Hello, my name is Bomsaerah Song, and I am a senior majoring in chemical engineering, working on the computational study of ammonia synthesis on metals in plasma conditions under Professor Diego Gomez Goldrin in the Department of Chemical and Biological Engineering. Ammonia production is essential due to its application on fertilizers. The current ammonia synthesis method of the Haber-Bosch process requires high pressure and temperature, which is not compatible with the renewable energy. Plasma catalysis is an alternative method to perform the ammonia synthesis process at lower temperature and pressure, but it has not been fully comprehended. To better understand this alternative method and optimize the catalyst with experimental data from collaborators, we studied the interaction and reaction of nitrogen and hydrogen plasma species on a variety of metal surfaces, including transition and low melting point metals using density functional theory method. Figure 1 shows the reactions that could happen under plasma conditions for ammonia synthesis. We studied several different catalysts, which were divided into traditional metals used for industrial ammonia synthesis, such as iron and nickel, and some non-traditional metals, which were gallium, tin, copper, gold, silver, and palladium. First, we found a stable binding energy and site for ammonia-forming species. Figure 2 shows some of the most stable site for species on gallium surface. Since gallium metal has not been studied in many literatures, we calculated the most stable gallium surface. By using this information, we were able to calculate the binding energy of the intermediate reaction species and the reaction energy of ammonia formation. With these information, we were able to estimate the activation energies using the Bronsted-Evans-Pollini relationships, which can be found on Figure 4. Our collaborator, Dr. Maria Carrion from the South Dakota School of Mines, experimented that worst activation energy for thermal nitrogen dissociation performed better, which means that we don't have the rate determining steps. And this led to believing that Ely-Radial relations for nitrogen and hydrogen formation influences the catalyst performance. We plotted the turnover frequency versus the activation energy, which showed volcano-type relationship, which can be seen on Figure 5. With all these observations, we concluded that non-traditional catalysts such as gold and tin perform well under plasma conditions, and the competition between hydrogen depleting reactions and nitrogen hydrogen forming reaction are key performances to the ammonia synthesis. As of right now, we are observing energy barrier for NH formation using nudge elastic band known as NEB method. Figure 6 shows the NH formation on nickel surface, which showed low energy barrier. We are working on observing these reactions for all metal surfaces being studied. Thank you for listening.